We want to now go ahead and delve a little bit deeper into the concept of cache. I want you to exactly understand what happens when you go to a cache from the CPU. So the way to think about the cache is that you have your CPU. CPU issues commands like, for example, LDUR that require grabbing data from the memory. When you have an LDUR, you're trying to access memory at some position, some address. And instead of going to the memory, you are going to go to the cache, like I draw here. So that's what we mean when we say that cache sits between the memory and CPU. The CPU goes to the cache first. Now, just as a side note, a lot of times the cache is actually just inside the CPU. Physically, it's within the CPU. Right? So this is just like a conceptual diagram. Whether it's inside it or outside it, CPU goes to the cache. It asks it for this address A. Address A is somewhere in the memory and it's going to have some data in it. Okay, so now CPU comes to the cache and asks for the address. The way to think about the cache is that it's a table. It's a very large table where, in this table you keep some values from the memory. So, for example, the memory value from address A is kept here, and maybe, for example, this memory address, this memory location B is kept somewhere else in the cache. It doesn't have to be in the same order. Somewhere else you have memory B. Now the cache is a lot smaller than the memory, so not everything is going to be kept in the cache. So in this example, we are going to assume that this position C is not in the cache quite yet, right? So we don't have C inside the cache. In addition to keeping these memory addresses, it also needs to somehow or another be able to tell us what address in the memory does this position correspond to, right? So for example, here we somehow need to know this is position B, this is position A. Okay, so let's go back to our scenario. CPU has asked to do a load of address A. We come to the cache. We have to be able to ask cache whether the data that we want, address A, is present there or not. Two things can happen here. Maybe what we want is present in the cache, which is the case here. If it's present, you just send back that data to the CPU and you never actually go to the memory. We never make this trip to the memory. We just go to the cache and back. When this happens, it's great. We like this scenario. This scenario is called a cache hit. This is the scenario that we like. Why do we like this? Because cache is very close to, or maybe even inside the CPU, this round trip can be done very quickly. It's very fast. In fact, for some types of cache, you might be able to do this in one clock cycle, which is what we are going to assume for our design. We are going to assume when you go to the cache, in one clock cycle, when you need the data and the data is in the cache, you can go to the cache and come back in one clock cycle. That assumption is reasonable when cache is physically inside CPU. So that's the nice scenario. Now, what happens if here we are asking for address C? You go to the cache, somehow you look up at all the values that you have, or however it is, somehow the cache has to be able to answer, do I have C here or not? In this case, we assume we don't have it. When you do not have the address in the cache, what you have to do is you have to go to the memory, go to the right address, in this case, address C, ask the memory for that value, take that value, bring it back, and save it in the cache somewhere. Right? So maybe, for example, we decide to save it right over here. So we are going to, let's see. And now that we have fully saved that memory address here in this memory address over here in the cache, we can go ahead and send the data back to the CPU. This scenario is called a cache miss. We did not have the right value. When we do not have the right value, we have to go to the CPU, grab it, and bring it back. This trip to the memory is very slow. Then you have to go back to the memory, go to the memory and come back. This can take a lot of time. This could take tens of clock cycles, maybe hundreds of clock cycles if you're unlucky, right? So this is going to be very slow. And because it's slow, what does CPU need to do in the meantime? The moment we realize here that we have a miss, we have to ask the CPU to install itself, right? So as soon as we find out that we have a miss, we tell the CPU that it should install, just like it installs for the pipeline. It installs. It doesn't do anything. It sits there. It waits for the cache to go to the memory, bring back the stuff, update itself. When it has updated itself, it sends back the data, and then the CPU knows that it needs to come back to desktop. So you can imagine that all of this takes a lot of time, and because of that, when we have a miss, we say we have a miss penalty, meaning that we are penalized in terms of time. In your next slide, a lot of the concepts that I just described are written out. Each row in this cache is called a cache line. So all of these positions are called the cache line. Another important thing to keep in mind is that I didn't quite tell you how to design this table yet, right? I assumed we are putting things in specific places. Various designs for cache are going to make these decisions differently, and we're going to discuss them. The decisions are basically, how do you know if you have a hit or a miss? You have to have some mechanism to be able to answer that. You have to know where to put the data that you want to keep. You want to know how much data I want to keep here, because remember I said the data are brought back and forth in blocks, right? So when I went and brought this C portion from the memory, it can be that I bring not just one double word, but a bunch of double words, a block of double words, all at the same time. And I save them in the cache. How do you deal with that? Is another design decision that we have to make. As we progress through this chapter, you're going to see various designs that make these decisions in different ways.